Good morning. I'm Alessandra Carbone. I work at the CNR Institute for Advanced Energy Technologies. And in this, first of all, I wish to thank the organizer for this kind invite. And today I'm talking about the part related, the work package of the project related to the membrane development. This work was made in collaboration with the other partners of this work package, mainly Hydrolite, that was in charge of developing the membrane, and also Denmark Technical University and us, that were in charge of the characterization, the full characterization of this kind of membrane and the selection for the development of the 50 kilowatt stack. This is just the introduction about the membrane. We started for the previous project, and this project was an increasing of TRL from the TRL 5, that was the previous project, up to TRL 7. In this framework, membrane based on fully aromatic hydrocarbon polymer with the quaternary ammonium, and this is the only information that can I share, were developed by Hydrolite, and should meet the key performance indicator of the project, that are a target on anion conductivity that should be higher than 60 millisiemens, in the net temperature range 68 degrees, alcohol crossover lower than 10 milliampere per square centimeter, and a stability in a wide pH range, and a mechanical strength of higher than 20 megapascal. So an overview was, considering that this presentation is a summary of more than 3 years of activity in the project. So we tested a lot of membranes, and we started from membrane generation 1 that has very good properties, but has some issue in the scale up. So we moved to Gen 2 that mainly has the same configuration, but with some improvements. These membranes, Gen 2, we had 4 generations of Gen 2. At the end, Gen 2.4, we characterize 18 membranes that has different properties in terms of cross-linking and chemical properties. And one of these membranes was selected for the scale-up and the utilization in the 50 kilowatt stack that in this moment is running. So, first of all, with the Gen 1, the first characterization is the ion exchange capacity. And we compared with the Fumatech that was considered the benchmark, even if it was coming from the previous project. So the Fumatech ion exchange capacity was calculated, measured by immersing at room temperature, while the Hydrolite was calculated after immersion at 80 degrees in KOH 1 molar, and more than 2,000 hours, if I remember good, 6,000 hours were reached, with low degradation respect the benchmark. Then, with the other generation, it was studied the influence of ion exchange and concentration of KOH for activation of the membrane to have the full anion exchange and have all the groups in OH form, and different time and KOH concentration were carried out, and a protocols of 24 hours in KOH 3 molar, also in accordance with Hydrolite people that developed the membrane. These protocols was chosen, and it was also decided to have an ion exchange capacity of about of a value of about 2 milliequivalent per gram, despite the cross-linking, because this can guarantee the good anion conductivity and good performance. The first test in terms of mechanical test was a creep test in the elongation mode. we used the standard protocols that we have set at CNR that consist in stretching the membrane at 0.5 Newton, then a sudden increase to 5 Newton, and again for 1 hour, and again returning to 0.5, and this was set up for the benchmark. The membrane with generation 1 was successful for this test, while the other ones, all the other membranes, only the H9 that was from Gen 2.4 generation reached the complete test. So we decided that this, because the elongation was higher, the limit of the instrument, so we decided that this test was not successful just for the selection of this membrane in terms of mechanical properties. So at DTU, they performed with a different instrument, tensile strength in the machine direction. Here in the graph are reported all the membrane that were tested. I show with the mouse because online they can see. So all these membrane were tested, and here there is a comparative table, and we can see that only membranes H4 and H16 approaches the target, that is the target of the project, that is 20 megapascal at 60 degrees. This test was carried out at 60 degrees and 80% of relative humidity. And according to this table, we did a selection for further characterization, and 4 membranes were selected and tested also in the transfer direction. We can see that from the graph that the membrane H2, H4, H5, and H9, only the H4 reached the best tensile strength, approaching the 20 megapascal in both the direction, while the H9 has a different behavior due probably to an orientation of the molecular chain or some anisotropy in the membrane. Then the ion conductivity was carried out. First of all, the in plane by using a method of true OH that was well described by Professor Deckel, in which the membrane in bicarbonate form was directly exchanged upon a current feeding in OH. And also here we can see that in this graph, in the left graph, there is the comparison of the previous generation compared to the benchmark. The benchmark is the orange one that has the lower conductivity respect to the hydrolyte membrane. Here there are all the 18 membranes, but in this case, this graph is the conditioning of the membrane, and when the line reaches a plateau, it means that all the groups are converted. So after this, we started with the measurement of the anion conductivity, increasing the temperature. So in this graph, is reported the comparison among the benchmark, the previous generation, and the 4 selected membranes as a function of the temperature. And we can see that the membranes of Gen 2.4 show similar conductivity than Gen 2.3 and better than Gen 2.0, but also higher than the benchmark that is the lowest. Then at hydrolyte, it was measured the anion conductivity in the true plane section, and with the Scribner test station. Here are reported this test was carried out at 80 degrees and 95% of relative humidity by impedance spectroscopy. In the table is reported also the comparison of the previous generation and the 18 membranes, and it's clear that the Gen 2.4 has higher conductivity than previous generation 2.3 and 2.0, and H9 also in this case shows a lower conductivity. So this is very, very important. This test was set up at DTU and is regarding the CO2 crossover, because obviously, like in the previous question, crossover is very, very important. It can be detrimental for the performance. So at the DTU, they set up this method in which there was created MEA and tested like in an electrolysis mode. And here in blue are reported the reaction of hydrogen and oxygen evolution, but when CO2 is introduced to the cathode stream, there is the formation of bicarbonate. So the bicarbonate can migrate upon current with OH, and a mixed conductivity and a mixed movement of anion can arrive to the anode side. So it was measured, which is the contribution that we call electrochemically driven of the CO2 that migrates, it is pumped on the other side, or when we apply a current, or when the current is zero. This is only the diffusion, so physical crossover. So in this slide, in this graph, this is the reported for the benchmark. We can see that the electrochemically driven crossover obviously depends by the current applied. And when obviously in the cell there are two CO2 sensors to measure the actual amount of CO2, and the diffusion driven can be estimated as a 10 to minus 9 for the Fumatech membrane. The same test was carried out for the selected Gen 2.4 membrane and Gen 2.0 membrane. We can see that for the hydrolyte membrane, we reduced the crossover 1 order of magnitude because we reached the 10 to minus 10. And for the other membranes, the crossover is similar. In addition, in this graph, in which is reported the electrochemically driven crossover as a function of the current density, we can see that for membrane 2.0, 2.3, and H5, they has a low crossover than the benchmark, while the other two has a little bit higher crossover. But in any case, the value of the crossover, permeability crossover, as we can say, is in the order of 10 to minus 8. So it is not a big amount of CO2 that migrates on the other side. So it is not really affecting the performance. So in addition, we also studied the hydrogen crossover, because hydrogen is produced and we want to avoid that comes in the oxygen stream. So hydrogen crossover was also measured by preparing an MEA, like in a fuel cell mode, with feeding with hydrogen and nitrogen, and by a linear switch to oxidate the hydrogen that migrates in the nitrogen site. We can see that this is the graph reporting the data, and we can see that in general the hydrogen crossover is in the same order of magnitude for the hydrolyte membrane and Fumatech membrane, that is 10 to minus 9 mole for Siemens square centimeter. But generally, it corresponds to what is reported in literature for polyaromatic membrane, both in protonic or anionic environment. Then we also studied the ethanol crossover in the same configuration of hydrogen crossover, but only feeding ethanol solution with different, in KOH, 1 molar, with different concentration of ethanol, because these concentration were estimated according to the results that we obtained in the real operation. So we can see that with the membranes, except for H2 membrane, all the membranes has a little bit higher crossover than the target of the project, that was 10 milliampere. for square centimeter. The reason why the H2 has this very low ethanol crossover was because this membrane was hot pressed due to the inhomogeneity in the thickness. So the hot pressing helps to reduce compact the membrane and helps to reduce the ethanol crossover. Because some partners also found formate in the liquid stream collected by the test, also a formate crossover was measured in the same way of ethanol crossover, and we can see that the crossover in this case is very, very low and is below the target of 10 milliampere per square centimeter up to 0.25 molar. At this point, it was selected according to all the data that we have studied and considering a compromise between the mechanical properties, the anion conductivity, the crossover, the membrane H4 was selected for the stack realization and a scale-up was carried out. And 105 samples with the dimension 40 times 70 square centimeter were prepared and sent to Ito for the 50 kilowatt stack and were used and assembled. In addition, this is just to show you the performance at the lab scale of the membrane H4. This test was carried out at the CNR lab with the electrode nickel iron produced by CNR and the cathode produced by the NORA, and we can see a quite stable performance in 2-hour test, and the products are mainly hydrogen and ethylene, and by the liquid product that we collect, the most is ethanol. So, in conclusion, in this work package, extruded membranes made of fully hydrocarbon polymers based on quaternary ammonium groups, functional groups, was developed, was scaled up with a good stability in terms of anion exchange capacity, is very close to the target of 20 megapascal, considering the tensile strength, good conductivity of 276 millisiemens for centimeter at 80 degrees, and lower CO2 crossover, and also scaled up for the 50 kilowatt test. So I wish you thank you, all people online, and thank you. Questions from the audience? Yeah.
Thank you very much. Very interesting information. I have actually 2 questions. One is the about exchange time, exchange information. Could you please go into that?
Yes.
So my first question, how we check whether the exchange was full or not? Is it full? And the second question, have you taken care of CO2 contamination at the exchange stage? Because you have CO2 in air, you have CO2 in water, you have already taken care of that during the exchange, or if you say it's not going to contaminate the membrane until it's CO2 anywhere, we don't care whether it will be contaminated in the beginning.
Okay. The exchange, we consider, I answered your first question. We consider the exchange full because at Hydrolyte they have measured the ion exchange capacity of the polymer. If I remember good, with the NMR or something similar. So we have the nominal ion exchange capacity. So when we reach the nominal, it's okay. Then regarding the contamination, it is not reported here, but we also performed the anion exchange capacity in chloride form. And the titration of chloride, we reached generally the nominal amount. So in this case, we have a good accordance among titration in OH and titration of chlorides. So we believe that this is the full anion exchange capacity that we can reach. Yeah. Ah, it's blocked.
Thank you. So there is questions online. First one, why do membranes require such high mechanical strength? Is this for surviving self-compression or for resisting the CO2 electrolyte differential pressure of less than 1 bar?
Yes.
If you want to see.
Yeah.
If you want to read it.
Yeah. Okay. Okay, require high mechanical. Okay, this is a target of the project, but obviously it should resist the compression. In fact, in the first test of the stack, we suffered some broadening of the membrane, in particular in the framework. That is the typical broadening of a membrane when you assemble a zero gap cell. So to increase the mechanical strength during the assembly, and also obviously, of course, to sustain a differential pressure that can be during the operation. How the ethanol format crossover is quantified? What do the units mainly? Okay. Generally, we have a target of the project in milliampere per square centimeter. So I reported this target, but by the Faraday law, we also were able to calculate the moles of the ethanol and format crossover. In this case, if I remember correctly, the data, the moles are very similar between ethanol and formate. This is due to the different electrons that are involved in the reaction that are higher in the ethanol than in formate. So it is comparable in terms of moles, and is different in terms of milliampere, but is reported in milliampere per square centimeter because it is a target of the project.
Thank you. Thank you, Alessandra. This was a great presentation. It goes to show that we just don't have the membrane and we put it in the stack and measure. There's all the characterization we have to take care of and develop it according to what is required in the system. So that was a really good presentation to showcase that all the components that we have to consider for the development. So yeah, thank you, Alessandra.